I might have tried writing a Python strategy. But I still have the what? No, it's also double-sided. Which is I said I chose this on exclusively, yeah. You know, I had my first internship interview today. Pretty well. It wasn't much. Just asked me like golf problem. Off the verdict.
All right. So today we have some worksheet printouts. If you don't have one, there might be something still like hanging around the class. But if you don't, I still have some here. Yeah. Anyone don't have the worksheet? Okay. You have worksheet? Okay. Just spread it now to here. Yeah. Okay. Just take film.
Thank you so much.
Anyone who? Okay. Perfect. We all have it? Okay. Do you have the worksheet? You have the worksheet? Okay, perfect. So, please write your name on like one of the corner of the worksheet and with your just name and unique ID. And once you leave the classroom, just leave it on one of the chairs at the back. So. And if you don't have it, feel free to, okay, I'm going to leave some at the, you don't have it? All right.
We didn't know we were turning it in, sorry.
No worries. Yeah. So if anyone who don't have it, I put some extra here. Just feel free to come and grab it, okay? All right, let's get going. Before we start the lecture, little quick update on the class schedule, like logistic stuff. We have the the midterm and also the team formation location settled. It's for the 2 midterms, it's going to be at the DOW building, DAO. We have actually 3 rooms. We have like ranging from 100-ish people to like 40 or 70 people. We're going to spread it out later on, and you will know which room you will be belonging. But we have basically 3 rooms assigned for the midterm, 2 of the midterms, all happening at the same place. And for the team formation event at the 14th of February, it's going to be happening at the GG Brown, 1571, from 4:30 to 6:30. So yeah, that's the quick update. And today, we're going to talk a little bit continuous from the last lecture, and we're going to talk about like MMIO from the perspective of GPIO. So last lecture, we talked about the the APM advanced peripheral buses. Today, we're going to also finishing up what we started there, and then later on, we go to the anatomy of the GPIO ping and the method for driving different pings inside of the GPIO. And we're going to hopefully close by one of the examples that's currently on your worksheet of how we built a GPIO, I guess, an easier version of GPIO out of the things we already learned so far. Cool. A little recap here. So from last lecture, we kind of stop here where we talk about like reading data from a switch. And then what we noticed is that because we're humans and the switch can like take longer to be ready compared to other like registers or other hardwares inside of the chip. So we might encounter some of the gray area which we identified as unidentified, which is that gray area inside of the whole figure. And then that could very much take more than 1 clock cycle. And what we're going to do about that, it's basically what we call the metastability, which is because if that happens, the whole system is going to run into like an error state. And then in order to solve that, we put an additional like a synchronizer circuit. And there are a few different ways to do that. One of the easiest and probably most cost-effective ways is to just add 1 more D flip-flop, so that we have 1 D flip-flop that used to be, make sure there's something there and hold the previous data, and then the other D flip-flop handles what's happening on the hardware. And whenever that's ready, it pushes to the new one, and then on the receiving end, it's almost always something there. And of course, that means we will have, just like this, adding 1 more D flip-flop here, but that also means we're going to take 1 more clock cycle if you look at the graph there. So one of the clock cycle is going to be basically a wait phase. And, a lot of times that's okay, and it's kind of up to your design, whether you want to add this, or we will advise you to add this, unless it's something happens much faster and does not cause these type of issues. But there are also other ways to do this. This is the most, I think, cost-effective way to do it. Okay. And that was from like a single switch. And what happened if we want to read from multiple switches, right? It's pretty straightforward. So basically, we add you remember like previously, we did not connect the address to the D flip-flop because to the register because it's kind of not needed since there's only 1 peripherals there or 1 register there to deal with. But here, since we have more, so we're going to need that address ping now serve as a select ping for a MUX. Do you guys all know what MUX does? Like a multiplexer? It basically select one of the channels that's connected to and then put that to the output, essentially. And for here, we're going to use we're going to connect the address to the MUX to decide which switch we're currently reading from. It's usually just 1 bit to determine on and off for this one, although we connect the whole 8 bits of the address to it. This example specifically, it's basically the second index bit of the address. It's the selecting pin between the two switch. If we say the address is 1000 and 1004. All good? Okay, nice. And some standard notations when you're drawing one of these graphs. So you don't have to, for example, basically we have like the D flip-flop and registers. You can just draw one of them and say that how many bits that's inside of the register. You don't have to draw like 32 D flip-flop there. And for the buses that are going around the graph, you can also, if you look at here, basically say how many numbers of lines or how many bits of data that's currently being transferring with a number on it. You don't have to draw all 8 lines, or 8 or 16 or 32 lines there. And similarly here, if you want to do some concatenation of the data, you just spread it out and then mention which bits goes to which line. And for the AND gate and stuff, and you can just simplify it as a address masks and then tell that what's instead of drawing all the lines to one and then make a little circle on each of them to indicate which one is the selecting bin. And also we have the VDD and ground, basically representing the logic high or logic 1 and logic zeros. These are like some standard figures you're going to be using when you draw one of these graphs that we showed. And we're going to look at one of them together. Well, you're going to look at them all of them together. So for this one, let's draw something, I guess, more, which is all the reads from that read, that basically all the read command going to read from this one register, and all the write command going to write to this one register. And then I would like you to connect all those signals to the appropriate pings on this register, and then you should have this on your worksheet, like the first one. Feel free to talk to your neighbors, and then we can work them out together in like 5 minutes or so. These are some standard notations, and just in case you need some previous examples, these are how we draw this. You only need to draw the ones that's necessary. If it's not super necessary, you can just leave it hanging there. Does everyone have the worksheet? Anyone don't have the worksheet? Okay, perfect. There you go. All right, let's look at the graph together. Cool. I guess we will almost always start with the easiest one, and I can give it away to you, even during the class. The P clock going to be connect to the clock, and that's usually the case. So you have 1 free point here. What else? What do we do about the P read data, the top pin here? Any ideas where that connects to, or if we connect it at all? Yes. That is correct. Connects to Q. And what about the P write data? Yes. That is correct. And anyone have any questions regarding these two? Because we're doing all reads and all writes to this one register, right? So it just connects to the D and Q. Yes.
I just want to know why PD data has to connect to Q.
Yeah, because if you have like a D flip flop, that basically on the Q side is where it's the output of this register. You can think of that, and then that gets fed to the P read data, which then got acquired by the core. So yeah, okay. What about the next ones? P write or P, how is that connected to the 32-bit register? On the 32-bit register, we have the enable pins, clock pins, and D and Qs. So we already filled out 3 of them. We are on pretty good track. Any ideas? What do we do about the P write? Yes.
It has to be added with the key enable select symbols.
And then connects to.
And then connects to the enable.
And why is that? Why do we need all 3 of them?
You need key write to know that you're writing register.
Mm-hmm.
Both know that to enable one, select the writing one. So the enable register.
That is correct. So anyone have any questions regarding this? Yes.
If we were writing, I know it's just like a simplified example, but
Yeah.
if we were doing all of our writes to this register, would we need pselect?
Will we need pselect? That's a great question. So in the actual architecture, since the pselect is an individual ping, it's almost always, basically have one pselect to each of the register. So we will always, but that's a good point. In this case, it's always going to be high in certain, because that's the only register there is. But yeah, for the sake of hardware implementation, we just always have, because we always have a pselect to each of the register. Okay. Any other questions? Okay, what do we do about the P address? Yes. So you're saying we add another like AND gate or MUX between this AND gate and the P address, and then before we enter the enable. Is that what you're suggesting? Yeah. That's a very good thinking. You're thinking ahead. So these are probably, because for this simplified example, we have only one register, so everything goes to this register, and every output comes from this register. But what you're suggesting is going to be very useful in the next few slides when we have more registers to work with. So I'm going to just let you know this. We're not going to connect the P address to anything in this particular case because it doesn't really matter. Yes?
In regular notation, would you connect that P address to enable, or is enable just kind of a 0, 1 on and off?
You mean on the register?
Yes.
This is just an on and off. So in the actual example, like the actual real case, even the P address, there is only going to be one bit that's being dedicated to this enable, to this register. All other bits going to be mapped onto different registers.
So is there like a different component that you would route the address to that would let the register know about it?
That's a great question. Any additional components needed or any additional things we need to do to let it do that? We will go into that in the next few slides. But yes, we're gonna. Typically, we have additional like AND gates or some MUX to deal with that. So to make sure that we have either both of them have to be high, then it needs to be high, or we input one of the signal as high to the enable. But on the register part, there's only one enable ping here. Okay, and what do we do about the P-ready? Just these two, you guys figured out. What do we do about the P-ready? Remember, the P-ready is basically telling that it's ready to execute the next instruction. So basically, whatever is executing inside of the register is ready. So the register is ready to, the data that's being calculated or executed inside of the register is ready. That's the signal that output from the peripheral or from the slave peripheral to the master, as opposed to the P enable, which is the master sends out the enable, tell all the slave peripherals. Any thoughts on the P enable? Sorry, P ready. Yes.
We can and enable
Mm-hmm.
and the clock, so that when enable is active and the clock has already gone, so Q updates,
Mm-hmm.
they know that the data is ready.
That's a very good thinking. So essentially, it's as long as the clock is ready, the data is ready. Like the register is ready immediately, so to speak, right? Yes. I think that's the idea is correct. We have something even easier to that. We just connect it to the VDD for this case, so it always stay high, and then whenever the clock's in, it's a similar idea. It's just easier implementation here and save some power. Because in this case, it's the calculation is done immediately within like one clock cycle, and we just connect it to the BDD so that as long as everything before that happened, you're ready to grab whatever you want from me. So we're gonna look at some like non-immediate cases in like next part of the lecture. But this is this example. Yeah.
Can you period we're working on?
Yes, that is a very good question. So why is that only that part that goes high? So look at the before and after. Basically, the two line says it's the previous stable stage, which we don't really care. And you can think of this P-ready as what's the master register or like master peripherals point of view. Before that, although it's always connected to the VDD, it just doesn't care its value. It's only carried it when everything else is ready, and the P-ready is also ready. So that's the part where it became high. So on those two line periods, it's also high, but it just like it doesn't matter. Yeah. Yes.
So I'm still confused about the P.
Yes.
Why exactly it's that? Like,
To the VDD.
yeah. Like,
Uh-huh.
I'm just confused like what that represents exactly, like the whole line and that.
Yes. So the question is regarding why the PDD notation here and why we're connecting to it. So the couple of slides back, the notation means it's connected to the VDD, which is the logic high. So it's like always ready. Cool. Any other questions? Or we're good with this example? Perfect. We're doing great today. Okay. Okay. So next is just a couple other slides. This is okay. I hold on this. So this is the write transfer with the wait state. Basically, these happens when we need to, or like the peripherals needs to wait for slower things. For example, during like a write or read. This particular case is during the write transfer. So for example, you want to write it to some external device or external memories that take longer time, so that you will need to handle or let the master know that it's not ready. It needs a few more waiting state. So that's why you will see the P-ready here. It previously don't care, and then once everything's ready, it goes to 0 because it's not ready. It needs some time in order to finish the process. And then it goes back on again once that's ready, and then don't care again. So this is some case that when the P-ready is not always connected to the VDD. So essentially two of the wait state here, and then it's the ready state. We also have similar things for the read transfer, which is probably more common, to be honest, because you basically read data from, say, again, like either external devices take longer time, or like some of the configurations that take some internal calculation. For example, ADC channels, you will learn in the later part of the lecture. It takes the analog signal and then convert it to the digital, analog to digital converter. So that itself, it takes extra time for the convergence from the analog to digital. So these are what the waiting states can look like. And again, the P-ready here is not always high. It will tell the master to hold on, and then after I finish all these, and then it's good to take from me. Cool. And an ABP state machine, just in case you guys are curious, basically you can read it yourself, but the takeaway or like the good thing to notice is pretty much the requester or the master sets the p-enable high whenever the data on the bus is ready. And then the completer, each of the completer or slave device have its own data bus, the p-write data, so that whenever the core or the master needs to access to any of these peripherals, it's always there. There's no data collisions. And of course, the P-ready, which caused a lot of confusing, is basically whenever it sets the high whenever the data is ready inside of that register. Usually happens, I think quite commonly happens during like read data bus, for example. When that happens, when the data is ready, it sets it high. So that's like a pretty, I hope, pretty clear state machine on how each of these signals going to be turned on and off, and how they serve as the trigger of the whole purpose. Good? Okay. Perfect. Nice. So today we're going to look even from like previously it's like from the entire peripherals perspective, and the next part of the lecture we're going to look more specifically from like the GPIO's perspective, general port for like in and out, general purpose in and out. So again, I promise you that we're going to see this graph over and over again. We talked about this before in the class. Basically, it's the simplified architecturogram, and then we're talking about getting data in and out from the entire entire chip, and then how that's being handled with our bus structure. And in this particular case for the GPIO, it's it's from the what they call like the high performance buses, and then to the register banks. However, for this class, we're gonna just treat it as an APB, so that it's like a simplified or like simpler example. But the idea here is pretty much the same. We talk about the APB rather than talk about the higher performances. For the higher performances, they have some additional components in order to synchronize everything and make everything up to date. But essentially, they're using the same idea. So just some clarification before we go deep inside. And as a graphic representation, that's how it looks like on an actual chip. The previous graph where you found the GPIO to the core. And then this is the core, and that's probably one of the wires that connects to the GPIO. And then from your perspective from the board, some wires on the PCB goes to one of the pins. That pins mapped to one of the GPIO pins that you're dealing with when you turn on and off LEDs and other cool things. So also like a quick recap of what it look like inside. The boundary here, the navy blue boundary here, is basically the boundary of the chip ward and the outside ward. And then we have the in and out pin, physical pin there. And it goes inside. It have one of these, switches here, controls to tell if it's a input or output. And then if it's input, then the data goes in and it goes to the top and then goes to the register and goes to the core. And if it's an output, then the data goes to register out and then goes to the output control and then flash out to the in and out pin. So this is the same image here. So what that one was basically for the one pin. And when we start talking this structure that turns to registers, we basically have a bunch of this that we showed in the previous slides, and then concatenated this along one port, so that, for example, here the pin 0, like 0, 1, 2, 3, etc. It's kind of they just align along each other, and then how we access that is essentially have one of the designated input and output registers, so that each of these 1 bit is corresponding to one of the pins on these concatenated GPIO ports. For this specific ones, and also like one control pins, one control register for all of them. For this particular example, the zeros index pin that goes to control the zeros GPIO pin, which is the front one. So, any questions on this? It's essentially what we have on one pin, or like one port, one pin, and then concatenated into a theory of GPIO ports. Okay, hope that's clear. Okay, and if we look even closer to the anatomy of a GPIO port, like a single bit. Here is like a bunch of bits together. This is for one single bit, and usually have like 16 or 32 of them, but this is just a single bit. And we're going to look at the output part and the input part. We start with looking at the output part, which is the bottom part here. So it has the stuff that you were expected to have, and also we mentioned it briefly in the previous, I think the first lecture on the GPIOs. Basically, you have the output data register. It's a big register, but only 1 bit is going to this specific pin. basically this output register connects to all of those parallel put ports together. We also have a GPIO mode register, and this is also one of the, it takes more than one pin to do it. We can look that into more detail, but basically it controls mode of each pin. Is it input, is it output, is it analog pins, etc. We also have the output type register, or O-typer. It's basically controlling the output type of the register, that's output type of this pin. Is it, say, like a push up and push down, or is it basically which type of output you want to do on the output side of the GPIO, the I/O pin? So yeah, this is just some sample code on the GPIO mode register, what these two represent. Like if it's 00, it means input, 01 means output, etc. So this is like a very quick structure on the output side of the GPIO 1-bit. So if we look even a little bit closer, we have the clock enable register. This is essentially the clock pin that you connected to, and you will need to enable your clock if you needs to use or go to these peripherals. Otherwise, it doesn't have any clock. And the reason for that is mainly for like power. It's like a nice power saving method. You only connect the ones, or you make those connected only when you need it to. Otherwise, it will drain additional powers. That's not necessary. So it's also just 1 bit to either enable or don't enable. And this is like the code for that on how you. A lot of these are handled internally, but just in case you're curious. And the mode pin, a mode register, it's also inside of the GPIO peripherals. We actually have 2 bits for this, like we briefly showed before. So we can either have, and then, yeah. So these are the codes to do this. Basically, you put the, okay, actually. So we have 4 different modes here, right? There is a default mode for each of the GPIOs, just for the safety reasons. And the default mode is being put onto the general purpose output mode. The actual default mode is the input mode. And this is for the safety reason, so that the board itself is not outputting any current, or not trying to push any current into potentially anything that's connected to that pin, so that it doesn't accidentally break anything that connects to it. And if you want to set to a different mode, this is the internal code that does that. Essentially, it pushes the 00 to the previous to the 2-bit, so that it knows that it goes to the general purpose, and then you reset it to be the I believe 01. So you set it to be the general purpose in a general purpose output mode. These codes are again, just for the reference, these are how it's actually internally done, but a lot of them are handled internally. But it's good to know how they actually do that. Yeah, on the worksheet. Yeah. And just in case you're curious, we mentioned there are like some alternative function modes here, 10. And for these, it's usually GPIO specific. If you look at one of the, if you look at the datasheet of, say, our chip, you will see that some of these GPIOs also have additional functions to it, like the SPI or I2C, or like PWM. So these are all the alternative functions for this, for that specific GPIOs. And that's something you can set it to be. You need to configure it individually if you want to use that function on the GPIO, on that GPIO. Yeah, for example, UART. And we have the output type registers. So it's essentially determined between the, we have like the more more common ones, for example, the push-pull model, push-pull output types. We also have like the open drain ones. You don't need to know too much detail into this. This is very circuitry stuff, but essentially, the output pins, you can either push it high or low. Internally, it's connected to the VDD or connected to the ground. And then here, as we talked about before, you just think like the transistors, the two transistors there as switch. So the switch will be switching whether this pin connects to VDD or connect to the ground on the right. And if you connect to the VDD, it's basically pushing the current out of this pin, pushing energy, pushing power. And if you put it to the ground, it's essentially taking the current or taking whatever, taking the current from the connected device into your device. You can think of it that way, although they are all output pins in output mode. But yeah. And this is the, if it's connected to on the right, this is connected to the ground, and then it takes the current in. And we also have the open drain. It's one of the alternative functions, actually. It's basically, you have the half of the push-pull pair so that you can choose close or open this pin. And this, you don't have to know this by now, but basically this is pretty useful when we do the I2C communications in later part of the lecture. It's also used for some alternative functions. And there's also a way to set the output speed. So if you look at the curve on the right, and you can sort of determine how fast you want your pin in output mode to push up to the VDD. And any guesses on why we need to have this speed control, or like why is it useful to have something like this on the GPIO? Yes. That's a good thinking. I think yeah, that is certainly yeah, that's a good thinking. But if you just always make it super fast, then that would make sure all the clocks are taken care of, right? But yeah, but that's a very good thinking. I think, yeah, if you, yeah, that's a very good thing. I never thought about that. But yes, any other thoughts? Okay. Okay. Yeah.
Maybe for sending messages, we want to have the speed fast. Send faster speed, or you want it to turn off and on faster than turning on a switch. That doesn't matter if it's a millisecond slow.
So that it's, in case we're doing some like higher speed transmission, it's good to have these controls so that we, I guess, optimize for the power. I think that could be one of the reasons, actually. So yeah, there are a bunch of reasons for that, but normally it's used for, not sure if you guys know the term slur rate. It's basically the rate of the signal from low to high or high to low. It's essentially trying to protect or like trying to enhance, well, trying to make sure the connected hardware that you're interacting with is stay in a good performance range. Because sometimes if you drive it too high, too fast, you will have like a voltage overshoot, and then it causes like the ringing effect or cross-talking or like reflections between the channels. One, if they're doing like super high speed data transfer. So this is just some ways to like optimize the performance and the reliability of the system. So that's something they just chose to have it there, so that you know, you can be ensured that for the device that's connected to, it's being operating inside of its comfortable range. And there's also a lot of these went to like the electromagnetic interface interfaces, like the EMI protection, so that if you set it, always set it super fast, high and low, and if you know doing like high frequency signals, then the causes additional noises to other channels. But yeah, you're not going to be tested on this, but it's something good to know. Cool. And then there is output data register, or ODR. Basically, it's just writing to a pin. In this particular one, the upper 16-bit are reserved or not available, so you will be only using the lower 16-bit, lower 16 pins. And this is a example code again. It basically is set, how would you set the port B, GPIO port B pin 2 to high. And yeah, you enable the clock, you clear the mode bit, and you set it to output. And then you just select it to be the common output mode, which is the push-pull, and then you output the logic 1 to the drive. So this is like a sample code, all putting together little pieces from the previous slides. Yes?
Which language is this?
That's a very good question. I'm actually not sure. It looks like assembly, some form of assembly, but that's a very good question. Normally you would do C code, and then it got transferred into this code assembly. Yeah, I will check on that. That's a good question. Sorry, I will check on that. Okay. So let's move on to the input side. Or any one of you recognize this? Which language this is? Yes. It is. Yeah, it is C code. But then it's probably one. Yeah.
That was the ampersand equal operator.
Sorry, give me 1 sec. Yes, it is C code. You're correct. Yeah, it is C code.
I've never seen the ampersand and the equal sign operator. What does that do?
The ampersand and equal sign?
Ampersand and equal.
Oh, that's the bits operation. So you do this operation like a bitwise instead of the, yeah, it's the bitwise operation. Okay, cool. Let's look at the input side. So again, you know some like the normal stuff you will probably imagine. We have the input data register, and then we have the IDR, and then we have the pull up, pull down register. And we, in order to have the protection over, for the reducing noise for reducing the noise into this input mode, we also have something called Schmidt trigger here, so that we can handle the input. We'll talk about that in more detail in the next few slides, but basically that's something very useful to have if you have a lot of noises inside of your input signal. And also we have like the over voltage protection on this one, so that the additional power doesn't cause too much damage to your current board. And yeah, the push up and push down. So basically, they refers to the two resistors connected to your input I/O pins. They are essentially configurations for the GPIO input pins to ensure that the pin reads a defined logic level. It's like either high or low when there's like no external signal is driving the pin. And if we don't have these two registers, the pin is kind of like floating, and then it leads to like undefined or unpredictable behaviors due to could be like environment noises or other like a leakage current from our other device. And then we're going to talk about the Schmidt trigger, and just mentioned a little bit ago. So a lot of the signals, when you all know like analog signals can be noisy, right? But in fact, the digital signals can also be noisy. And this is one of the I guess examples here, that if we have a threshold, as you would probably imagine we did, to convert this signal to high and lows, then we might end up with something this. right? It's clearly not a clean signal. It's like fluctuating a lot, and that probably leads to not very good behaviors inside of your core or other peripherals you're interacting with. And with the Smith trigger, instead of one threshold, it basically have two thresholds. And then it's looking at the high threshold and the lower threshold to make sure it only when the signal that goes above the higher threshold, it's high, and then only if it goes below the lower threshold, it becomes low. So this would be in the middle. It's what that signal will look like. Obviously, that's a cherry-picked signal, so it looks perfect. In the real life, you will likely do some other processing onto the input pins, like some other pre-processing parts in order to handle that. But this is just how they did it on the like hardware level, which is easier to do. And yeah, this is an actual real signal from I believe a button push. A button push. So you can imagine a lot of, for example, this part will be get rid of. You can see my cursor. But with the Schmidt trigger, and then also this part. So it will look cleaner as a input from the button. Okay. Are you all good at this point?
So you put the upper trigger,
Uh-huh.
for the other trigger.
Yeah.
You put the upper trigger
Yeah.
right above the highest.
Yeah, for example, it's somewhere here so that when this happens, it doesn't go back to high again. It just stay low here, and then it became essentially this, and the clean down, and then up, and then clean down. So these little hairy stuff, and also little bump here, they got rid of. Yeah. All right, so yeah, this is like a quick the quick slides on other additional functions on the GPIOs, like the alternative functions we mentioned. ADC, DAC, these stuff you can deal with more later part of the lecture, and then how you're going to interact with a lot of other devices you connect your core board to. And then communication protocols, as well as PWM, which is very useful when you do, like, say, motor control, etc. You try to decide how fast or how many power it goes to a specific device. And they actually also have the op-amp ones, but it's going to be less of those with our class. It's much more circuitry or like analog compared to most of the signals we deal with. Okay. Any questions so far? Perfect. Next, we're going to look at one examples together, and it's also inside of your handout. So for this example, it's basically we're going to be looking at building an ABP peripheral as an example of the GPIO peripheral. And for the simplification here, we just put the GPIO crossed from the high performance ones and move to the normal ones, so that it's easier to do. But it's not that easy, easier. So this is how I think this is from one of the previous slides. This just give you like an idea of how it looks like from the higher level. Basically, we have the core on the left side. The core talks to the ABP bridge, and then it sends out instructions from the code to the requesters, which is here, the ABP bridge. And then the requesters initiates all the bus lines, all these colorful lines that we talked about, and then send the data through the bus. And then we have the completer, or the slave device here, which is, in this case, our GPIO. And then it got connected to a physical in and out pin. And this is only, again, one individual pins, which then got interact with the outer world. So yeah, take a deep memory on this, and then our task here is for this example, basically go through all these input and outputs of the bus lines and then connect them up with these registers that we just talked about, like the in register, the ODR register, as well as the mode register, to determine so that we are able to control the zeros bit, or like the zeros ping of this GPIO in LP right there. So yeah, let me check. Okay, yeah, I believe you have these on your handout, and please work together, and then we will look at it together. Something might be helpful. These are like the standard notations from the previous slides, and then some of the register details that you may or may not need to know, but just tell you how many bits are needed for interacting.
That's for the enable though.
Because your address, let's say your address is.
Going back, repeat this on this one item. No, bro, I don't know you three down. So if 3 more wouldn't help me break even.
So you set this maximum.
I used to break even.
If it's the same as this address, say since it's high section, then your high section is
See, look,
I get it.
their username on GPIO.
PR data.
ODR, MMIO.
Your PR data is the
There's no enable section.
It's alright, that was me.
So you have
I thought it was like, what? I thought it was massive.
If I just said very easy.
Oh, you're right.
Yeah, don't need.
Wait.
Because on top of the GPIO is set. It's like one for every So wait, this is open.
Repeat enable and you select. That's pretty much it.
Yes.
I don't know this word, but I don't know mine.
Arguably, I didn't either.
Oh, I just saw this on Discord.
You're saying these selected.
I did. I can look up.
A little bit lower. You're saying it doesn't.
And use a selector. What do we change? No, we have the power. Oh, I get it. No, but no, I don't get it actually.
But you're getting
Can you explain it?
the register. What is the Is it not like you're like?
What is our?
Yeah, it's correct. And then.
We did the same thing for P-cell. We did the same thing for P-cell. Bro, you agree with him?
I agree with what is on his paper right now. I agree. I agree. I was questioning why they needed more this, but I agree with that. Thinking what she says is so clear.
Why would you vehemently just agree with this?
Because this was, I'm saying, I was disagreeing. I said this at the very start, and then you were like, no, it needs to sell it.
As you discussed,
Well, you're already down to like $2.
Hi Hi guys, sorry, I just noticed that on your printout, it might be some little detail missing. There's a little pin here as well, like a control pin. I'm very sorry, that was not, might or might not be on your print list. There's an additional control pin here on the control, output control. Imagine those are essentially the two switch that's determining if it's input and output of this GPIO.
Oh, you're saying this is
I bet you. No, that's not a bus.
Okay, I'm gonna give 1 more minute, so trying to wrap it up, the discussion, and we'll look at it together.
Oh, you're saying correctly, goes there. The arrow right there is to GPIO, and then GPIO one
What would GPIO order?
That's okay, so.
I'm actually, that would make no sense. Arvind also said that, yeah,
I said.
yeah, you're on your own. Jason's erasing it.
Okay, let's look at it together. What's the first thing you connect? What is the first thing you connect? Yes. Sorry. Before even anything, what's the first thing you connect? Yes. That is correct. We connect the clock to everything, right? In this case. Okay, you have 1 point. Cool. Let's then look at one individual. What do we connect, or what needs to be connected to the P-write data here? Any thoughts? Yep. Like the output register. That is, and anything else? Wait, sorry, where is the P-write data? Oh, no, sorry. We only look at the P-write, the P-write data for now, yes. And it needs to connect to this one. That is very correct, because that's the data needs to go out. What other information are encoded inside of this? Yes?
Also connected to the input on the mode register,
Input, and why is that?
because you might want to change the value of the mode register when you configure it.
That is correct. Imagine this, remember this is an MMIO. It treats everything inside of that one, all those data are inside of that one register. So this data contains the data you actually need to output, for sure, and also the mode setting configurations inside of that as well. And how about the input register? Do we connect it to the input register? Yes.
Does the Q connect to the read data and the P connects to the output of the IO key?
Oh, we're not looking at the queue yet. Let's look at the like the write data for now. Where else does it connect to? Connects to the read data.
Oh no. Yeah, it reads data. Does the queue connect to the P read data?
Yeah, the queue on the input register will be connected to the PR data. But okay, let me just give this out of the way. So the write data register, the data 32 bits is going to be connecting to the output register as well as the mode. And the reason it does not connect it to the in is because that one is an input only. So it's going to come from our port to wherever it goes. So speaking of that, what we gonna connect it to the P read data here. This is, remember, the data that needed by core or by the master. What do we connect to that? Or which of the registers here we connected to that? Yes? The ODR? Because that's the output register that needed to be later on, well, not trying to give it away, but later on, be output through the IO pin to the physical world. In our case, we're doing the zeros bit only, but the data connects to all of them, basically. Okay, so what connects to the P read data? Second one, which of these registers needs to be connected to that? I'm going to let other people's talk for this one. Any other thoughts? Any thoughts, I guess? Yes. Yes, that's for sure. Anything else? The input register will probably be connected, right? Because that takes the data from the outside world and then has to find a way to put back to the master or the register, right? Okay. So actually, we're connecting all three of them. And why is that? Because I guess for the question, it would be for the mode, because it's also good for the masters or the core to know that which current mode it is inside of this GPIO. That's why all these will be connected to and how, right? We have three of them, and then we only have a 132-bit register. How are we going to do this? So we're going to need a mask. Multiplexer. We're going to need a multiplexer. But what's did any of you get this? I think when I walk around, I see like at least 2 people got this part. They know there's going to be more than one channel connected and also have the mux ready. So the next question becomes, what's the control signal or what's the mux select for this mux, right? Any thoughts? We can take a minute to discuss. Now that we know this is how it looks like. And also just give this way to you. No surprise. Okay, any thoughts? What we're going to use for as a mux select signal here for that one mask? Any thoughts? Yeah.
Some of the bits from the address, so not the two connected ones, but then the next three ones.
Yes, that is very correct. So the address here is going to be used. We're actually going to just use like 3 different masks here to just be easier. Connect to that and then, oops. But I guess you probably figured that out. It's always that case. You need like 3 pins there to determine some of the enable. We're going to then connect that to the mux. But before that, let's also look at the enable pin here. We have the right enable and select here as previously all the examples, right? They go into one AND gate, and then that gonna somehow goes to the enable. And anything else we need to do before that, now that we have multiple registers we're trying to control with essentially one address here. Any thoughts? Do you have a question or you have thoughts? Okay, later. Any thoughts? Sorry. Yeah.
So I think the AND and also the AND mask.
Mm-hmm.
With another sort of AND gate for each enable.
Mm-hmm. Mm-hmm. That is very correct. We're going to need an additional AND here that goes to these two, and those two AND connect individually to the enable down here. And conveniently, all those 3 inputs before that we talked about from the address goes to the control pin of the mux. Is it looking reasonable to you? Or you think some of this just made up? It doesn't work that way. Does this make sense to you so far? Okay, great. So you might notice that there's something still missing here for the input register, right? So what are we going to connect to do those? For example, what's going to be connected to the D on the input register? Yes?
Is it the IO from the IO pin?
That is very correct. So basically, the input from the outside world goes to the D on the input register. And then since it's only 1 pin, you just add little 0 there because we're doing with index 0. Small details, but get you 1 point more. Yes?
If the IO pin can only carry 1 bit,
Uh-huh.
we have 32-bit registers.
Because of the 32-bit register contains a lot of other information. This is one register to control a bunch of GPIOs, not just for this one GPIO. Yeah. Yeah.
Why are you writing the same data to the output data register and the encoder? Why isn't there like a multiplexer on choosing between the two?
For the, which part? For the write data?